Hello, this is Eric from UNC Charlotte. Today we'll have the first part of a crash course in C++ programming. This crash course is intended for people who already know how to program, but who may not be up to speed on how to program in C++. Maybe you already know how to program in Java, or maybe you know how to program in Python or JavaScript or something like this. Many people learn how to program in C, but they may not have learned how to program in C++. Many people have done a little bit of C, maybe they used it as C with some additional library support or something like this, but they never really jumped into the language itself. This crash course is not intended to be the be-all and end-all of C++ programming. It's really meant to bring people up to speed on how to program modern C++. It's to make them aware of the most common forms that they would use in C. In particular, C++ has evolved significantly since 2011, when C++ 11 came out. But lots of courses, tutorials, and codes we find online are still written as if C++ was stuck in 1998. But modern C++ can be just as expressive and easy to program as Python. There are a few things to know, but once we know how things work, C++ can be a very pleasant language to program in. Today, what we will do is to look at codes and look at what they do, and all the codes that you see are available on GitHub. If you want to know more, I can suggest you a few things that you can do. You may want to check out the various keynote addresses that have happened at a conference called CPPCon. You'll find them on YouTube fairly easily. In particular, you may want to check, I think about 5 years ago, Kate Gregory's had a talk called Don't Teach C, which was a call to people to teach C++ directly without teaching C first. And it's pretty good at presenting the basics of modern C++ and why we want to write modern C++. You may also want to check out a book by Bjorn Stroustrup. It's called A Tour of C++. Once again, it's not meant to be a complete guide of everything in the language. It's meant to give people an idea of what you can do and why the things work. I'll put links to all of the things in the doobly-doo. And with that in mind, let's get started. What we will do today is essentially look at code and look at what the code is doing. And so C++, it's a compiled language. And that means that we'll have a compiler. Here I'll be using GCC. It's GCC 8.3. I'm running all that code on a Debian machine. It's a Debian 10 something machine. It's important to have a somewhat recent compiler because C++ has changed a lot recently. And I think all the things I will be presenting are mostly from C++ 11, 14. Some things maybe from C++ 17. There is a recent C++ standard that came out about a year ago or so, but many compilers don't quite support it yet, so I won't really be talking about that. And what we'll do today is really the basics of C++, things that most likely you already know, just to make sure that we're on the same speed and to see how things go forward. So today we'll talk about the basics. In future videos, we'll see more complicated things. All right. So what we have on the left is a piece of code which is meant to just demonstrate how variables work in C++. The structure of C++ code is typically always the same. At the top, you end up having includes, which are the way you include libraries. Your main function works pretty much like it would in Java or something like this, returns an integer. And here we have that piece of code, and that's pretty much what you would expect. Syntax looks very similar to Java. You declare a variable by having a type. You give the name of the variable, and then you can give it a value. Let's look at what this particular code does. All right, so I'll compile the code. Here I have some scripts, some make files that have been set, so that I can just call make and it makes them. I compiled everything with C++ 2017, and I generate a binary, and that's what the binary does. So the first thing that we do is to declare an integer and print it. That's what that does, and that's what it does. It prints it. Then we do the same thing with a character, and that's what it does. We also have floating point number kind of things, and so we can print them. We have string types, so we can print strings directly, and that's what it does. One of the first things that maybe you're not completely aware of is that whenever you have a variable that that you do not initialize, it does not have a default value. In many languages, like Python or Java, if you don't initialize a variable, it has a value of 0 or some default value. It is usually not the case in C++. When a variable is not initialized, it's not initialized, so it has as a value whatever was in memory at that point. So if we just declare a but don't initialize it, and then we print it, then we will get some random value that shows whatever was in memory at that point. And here what we have is this big number. And if I run the code again, maybe I'll get a different value. Here it is. I got a different value this time, because whatever is in memory, there is something, and who knows what that is. So in C++, you usually need to initialize your variables, or bad things could happen. You have other primary types. You have Boolean types, for instance, that you can use. They can be true or false. And when you print them, they actually get converted to an integer to get printed. You can notice that to end lines, there are two ways of doing that typically in C++. One of them is by printing \n, which is literally a new line character. Or you could send this special thing called stored endl, and essentially the difference between those two things is whether you flush the output or not. If you want to know more about that, you can go ahead and follow that link and see what's happening. In C++, the main function returns an integer. It's actually used by the system in order to decide whether the program ended correctly or whether it ended with an error. In some cases you care about this, in some cases you don't. That really depends what you do with your code. So that was the first example, types. Let's look at the second one. The second one is about control structures, and there shouldn't be anything in there that should surprise you. Let's have an integer, and we can test if that value is 12 by using that equal operator. And we can see that we entered the if statement, so it was true. We can do it again. Here the difference is that we don't have curly braces. We went through it as well. The difference between whether you have curly braces or not is if you don't have them, then you only execute the next line only is inside the if statement. C++ is not a language that is sensitive to white spaces like a language like Python would be. So you need those curly braces to denote the block of the if, and if you don't put those curly braces, then only the next statement is going to be accounted for. Here the next statement is actually a warning for you. Be careful that if you put only a single equal, that will not generate an error in the compiler. What that will actually do is change the value of a and give it 0. And because 0 is false, we can see that we did not enter the if statement. And the value of a has actually changed. And that's why in many cases what you will see is people will write literals first whenever they do an equal test, so that if they mistype it and they put an equal, then that would become assign a to 12, and because 12 is a constant, you can't do that, and that would trigger an error, a compiler error. And you can see that the value of a has changed because we did not print yet another something. So that happened. The next control structure is a while loop, and that's pretty much what you would expect. Here we do is while a is less than 15, what we'll do is print a and increase a, and because we've set a back to 0 on this line, we expect to see values from 0 to 14. Here you go. That's what we expect. In C++, you have both a++ and ++a. On integers, they're pretty much the same. You know, it's a pre-increment, post-increment kind of things. If you actually apply ++ on a non-primary type variable, something like an object, ++ pre-increment and post-increment could behave slightly differently. If you want to know more, go ahead and read those links, and you'll know more about it. Fundamentally, that's a while loop. That's pretty much what you expect. Followed by that, we have a do-while loop. The difference between a while and a do-while is that you always enter do-while at least once, whereas in while you don't, and that's how do-while loops work. And yes, you do need that semicolon after the while in a do-while case to make it work. Or you have for loops. For loops work, I suppose, like in most languages. It's these three statement kind of things. That's the statement to initialize, that's the statement to test whether you keep looping or not, and that's the statement that you do at the end of each iteration of the loop. And so this is going to do, once again, the same thing. It's going to print a for all a from 5 to 10, which is what we get here. All right, so let's look at the next one. The next one is the how do we iterate over collections. Here I picked a collection from the standard library of C++. It's a vector, so it's a self-redimensionable array. Here it's an array of integer in particular, and we initialize it with 3 values, 3 to 1, and we can go ahead and print these values. And we can do that simply by listing all the indexes that are available and accessing v of I. And when we do that, we actually print the different values of v of I, 3, 2, and 1. There are other semantics that we can use. They are ranged for semantic in C++. That allows us to check all the values that are inside of the vector, and they come in the order in which they are stored in the vector. And that also gives us 3 to 1. There are other form of collections that are defined by the standard library. We have linked lists that are stud lists. Here I initialize a stud list with 6, 5, and 4, and we can do ranged for on them just in the same way. And a lot of things are iterable in C++. For instance, strings are as well. So if you have a string s, which is something, then you can go ahead and list all the characters that are inside of that string, and you can see it prints something one letter at a time. All right, range 4, nothing particular new in there. The place where people start getting confused about C++ and where they start believing that things are difficult is when we start talking about pointers. What we'll see is that there are actually few reasons in C++ to actually use pointers. Most of the time people use pointers because they need to either do dynamic memory allocation kind of things, and actually you don't really need pointer in those cases, we will see in most cases. Or they will use pointers in order to interface with C libraries, and we'll see that yes, in those cases we may need pointers, and that's why we may need to understand them a little bit more. All right, so how does pointer works? Here we define 2 variables, a and b, and we define a special variable. It's a pointer. The way to read those things is you read them from right to left. So the star means that it's a pointer, and so it's a pointer to an integer. And what that means that a variable is a pointer is that the value that it stores is the location of an other variable in memory. In Java, that's what you would call a reference, for instance. And you extract the address of a variable by putting that ampersand in front of it. So here now we have p. P is a variable, and the variable the value that p stores is the address of variable a, and that allows us to do things like change the value of a by using that variable p. So literally what we say is go to the memory location that is stored in P, and at that memory location, change the value so that you write 30. And so that's why once you execute this line, if you actually print the value of A, the value of A is going to be 30 because that line changed it, because P points to A. I mentioned before that in C++ we rarely use pointers. It happens, but it's actually fairly rare. In practice, people use a lot more references than pointers. And the semantic works the same in references. You read them from right to left. So that variable r, it's a reference to an integer, and it's initialized with A. And what that means is that if you set r to, let's say, 40, and then you print the value of r, A, and star p, then all of these values are going to be 40 because r, it's a reference to A. And so whenever you execute that r equal 40, you actually change the value of A. One of the benefits that you have of using pointers instead of references is that pointers can be remapped. So if you change P to now store the address of B, whenever you're going to write on star P, you're actually going to change the value of B and not the value of A. Here you see that we go ahead and we change the value of star P by writing 40 in it. And now if we print all the values of R, A, B, and star P, you will see that all of them are going to be at 40. The thing is that while we can remap pointers, references can't be remapped. Once we have chosen what variable a reference is referencing, then you cannot reference a different variable. It's done. It's a done deal. Whereas pointers, you can actually remap pointers to point somewhere else if you need. The way you can think about pointers is that essentially they are indexes inside memory, in the same way that if you have a large array, you can index the different cell of the array. The pointer is essentially the same thing, except the value, the array that you're accessing is memory. And the pointer itself is the index inside of that memory. And you can actually see that because if you print the actual value of P, not the value that P points to, the actual value of P, the actual value of P, it's an array somewhere in memory. You can see it's a 5A88. And you can actually see that if you print the address of A and the address of B, you'll see that the address of B is also the same. It's a 5A88. It's because P actually points to A. It points to B. And you can see that A is actually fairly close in memory. It's actually, it should be about 4 bytes away. Yeah, A is 4 bytes away from B. And that makes sense because those two variables were declared in the main function, the one after the other. And so they'll come close to each other. They're actually both of them in the stack of your application, which is where local variables get stored in C++, and I suppose in most languages. There is a difference of 4 between the address of A and the address of B, because on my system, integers are actually 32 bits. There is no guarantee that integers are 32 bits. That being said, on most modern machines and with most modern compilers, ints are going to be 32 bits. But there is no actual rule that says that they have to be. One of the reasons why people may want to use pointers is to be able to change the location that they're pointing to, or to do pointer arithmetic. You can do things like access p plus 1, that would be the next integer after wherever p is pointing. And you can see that p plus 1 is going to be 5A8C, and that can be a little bit confusing. You see that P was 5A88, and when you added 1, you went to 5A8C. And the reason for that is because the semantic on pointers is that whenever you add 1, what you're actually saying is points to the next thing that can be pointed to. And because p is a pointer to an int, and int are 4 bytes, whenever you do p plus 1, the address that gets pointed to increase by 4 because ints are 4 bytes. And that's why in C and C++ you can get nasty bugs, such as buffer overflows, buffer underflows, or having dangly pointers, because you can do things like that. So if you write something at the address p plus 1, then you're not actually changing the value of b. Like p was set to b. If you change the whatever gets stored at p plus 1, it's not actually going to change the value of b. It's going to change the value of the integer or whatever already is stored there, which is 4 bytes away. And in this case, p plus 1, it turned out that it's a. It's not guaranteed that it's going to be a, but with this particular compiler and in this particular case, it turned out that it's a. And so if you change the value of whatever is stored at memory location p plus 1, and you change it with 1, then you can see that the value of b did not change, but the value of a is changed to 1. That's not a behavior you can rely on. That depends on compiler, it depends on machine, it depends on a lot of things. But that's the type of reason why you get buffer overflow, buffer underflow, and those kind of nasty, dangly pointer problems that you typically get in a language like C or C++. So if p is a pointer, which is just a variable that's stored somewhere in memory, does that mean that we can get a pointer on a pointer? And the answer is yes, we can do that. P, it's a variable in memory, so e of p, that's the address of the pointer, and you can see it's close to b. It's a little bit below b, and that means that we can get a pointer on the pointer p. And once again, the way you read those type is you read them from the right to the left. So it's a pointer to p. You read it from right to left. And so we initialize pp with the address of variable p, which means that we can change where p is pointing by dereferencing pp. And here what we do is we dereference pp, which is p already, and we write there the address of a, and then we can dereference the dereference to pp, which is really variable a, and write 12 in it. And now if we look at what we get, we see that p has changed to now point to a again, and the value of a has changed and is now 12, and the value of b is still 40 as it's been before. Something else that we can do on variables in C++ is to declare variables to be constant. And here we have a simple example of that. We have a variable a, we initialize it with 12. We have a variable b, and we say it's a constant. We initialize it with 13. We have another variable c, we initialize this with 1. What happens is that we said that b is constant, so if you try to execute something like b equals 14, you won't be able to do that. The compiler is going to stop you. I can show you what the compiler will tell you if you try to do this. If you try to do this, it will tell you you cannot do that because b is a read-only variable. So you can't do that. The compiler is going to stop you. And so that means that we can still get pointers on those things. Here we have a pointer p that's going to point to a. And if we want to get a pointer, the pointers can be constant too. And once again, the way to read that is from right to left. So that's a pointer to a constant integer, and we can actually do that despite the fact that a is not constant. And the reason we can do that is because we can always take a variable and make it more constant, but we can't do the reverse. So we should not be able to to do this and to do star isConst equal 14. If we do that, we'll get a compilation error that's gonna look something similar to the error that we got there. And I wanted to point to you that the way these things can be written, they can be written in different way. Typically, people in the C++ community prefer this writing because it's consistent with the reading from right to left ordering. It's a pointer to a constant integer, and that's the convention that people call isConst. It's isConst because the const come from the right side, but actually this is actually the same thing. It's also a pointer to a constant integer. And note that the position of the const matters, because if you put the const after the star, then what is constant is the pointer, it's not the variable that is being pointed to. So while this is a pointer to a constant integer, that is actually a constant pointer to an integer. So that means that you can actually change the value of a by using this pointer isConst, but you can't actually change the value that this pointer points to. Like you can actually do that, but you can change the value of a by using this pointer isConst, but you can't actually change it. You can't actually change the pointer itself. And so finally, it means that you can get things like this. Once again, you read it from right to left, so that's a constant pointer on a constant integer, which means that we wouldn't be able to do either of these things. Finally, we can use const on references as well. And once again, they read from right to left, so that's variable cr. It's a reference on a constant integer, and that allows us to potentially read the value of a through this cr. But if we are trying to change the value of a through it, then we would get some kind of a compilation error. All right, a quick reminder on how type works in most languages. So here we have an integer a. We initialize it to 0, and then what we do is that we do those loops. What those loops do is do 1,000 time, do 1,000 time, do 1,000 time, do 3 time, increment the value of a. And so we expect that we'll be doing those things 3 billion times. We do it, that's 1,000 time, 1 million time, 1 billion time, 3 billion time. We increment a, so we expect a to be 3 billion. And we can see that it is not. A is not going to be 3 billion. I believe that should be a negative 1.2 billion or something like this. Yes. And the reason for that is because integers in C++, they are not arbitrarily large, like they could be in other languages. There are languages where there is no limit to the kind of integers that you can store. In C++, those integers are stored in 32-bit by using the 2's complement representation. And what that means is that the integers that you can store in 32-bit, they are going to range from negative 2.1 billion to positive 2.1 billion. And whenever you overflow this value, what happens is that if you're trying to store 2 billion something 48, then the value that you're going to get is this one. It's the lowest value of the range. The range loops on itself. And that's because of the way integers are represented in memory. All right, let's look at how floats are represented as well. So here you have a similar construct. You have a 3 loop, so do 1,000 time, do 1,000 time, do 100 time, f equal f plus 1. So we did 100 million f equal f plus 1, so we expect f to be 100 million, and the value that we get is 16 million. it's not 100 million. The reason why f here is not 100 million is because decimal numbers in C++ are usually represented in floating point representation, whether that would be in 32-bit or in 64-bit or in half precision, but they are represented using floating point arithmetic. And what that means is that the precision of arithmetic that you have is going to change depending on the magnitude of the numbers you're trying to store. And roughly whenever you get to the scale of 16 million, you get to the point where the precision of the arithmetic is larger than 1. You can't represent a difference of 1 at that scale. So whenever you try to add 1, nothing happens. Not really changing the value. If that surprises you, I suggest you read this paper. I think it's the actual paper is called What Every Programmer Should Know About Floating Point Value, and then that detail a lot about why the things happen in floats and what you need to be careful of and what you need to know whenever you program things with floating point numbers. Finally, here we have a couple of variables, x and y. They are of value 17 and 5, so if you divide 17 by 5, what you get is 3. You do not get a decimal number out of divisions in C++. You get these things are integer, so the division is an integer too. It's rounded down. It's rounded closer to 0, I believe. And you can get the remainder by using the modulo operator, and that expresses the fact that 17 is 5 times 3 plus 2. In all cases, I believe in C++, operators stay in the type that is more general. That means that if you do an int plus an int, you're going to get an int. If you get a 32-bit integer plus a 64-bit integer, you will get a 64-bit integer as an output. And if you do something like take an integer and multiply it by a float, what you're going to get is a float, and things of that sort. There is no convention in C++ that ints have to be 32-bit. That actually depends on your machine, and it depends on your compiler. On some compilers, ints can be 16 bits. In some compilers, they can be 32 bits. In other compilers, they can be 64 bits. And so because of that, you will see often people use types that are explicit in how big numbers are. You see that int32t, which means that you want to store a 32-bit integer that is signed. It can be positive or negative. And you will see people use unsigned integers also explicitly, so that uint16t, that would be a 16-bit unsigned integer. And if you're wondering how you do things like this to work, there is a construct in C++ called typedef that allows you to rename types or to create new types for anything. So what that does is that it creates a new type. The new type is going to be called my_type. And my_type, what it is, actually it's a float. And that allows you to do things like this. We'll see that in C++, it's actually a language that is strongly typed. Once you have a variable, and once it has a type, and that's the type of the variable. And it's actually very helpful in order to be able to decide to use the compiler in order to find bugs in code. But in many cases, you don't necessarily know exactly what the type is going to be, because out of the context, it's not necessarily super clear what it is. So what you can do is use the keyword called auto that will figure that out automatically. So here what we have is auto something equals 12 divided by 4. And so the way C++ is going to resolve the type is to look at whatever 12 divided by 4 is. And so it's an integer, so it's going to substitute auto for an integer in this particular line. Something it's going to be an int, so you can print it and you'll see it. You'll see it here, and it's going to be just fine. Note that it's not because you write auto that you can change the type of something. It's still a strongly typed language where variables have one type and they don't change. Auto doesn't mean that you have some kind of a variable typed system in your language. It just means that you tell the compiler, I don't want to tell you what the type is. You already know what the type is, so use that one. That means that if you are trying to assign a string to something, you will not be able to do that because something is fundamentally an int. It's the compiler decided on this line that something was going to be an int. And so you can use auto to do these kind of things all the time. If you take the address of something and you declare that variable as auto, then something else, it's going to be a pointer to an int because something is an int. We know that, and you take the address of that, so it's going to be a pointer to an int. And you can see that that yes, C++ recognizes that as an address. You can do that. Auto has strange behavior around references. So if ref, it's a reference to an integer, to the integer something. If you do auto foo equals ref, I would personally expect foo to be a reference to an int, and that would be something. It turns out that's not what C++ does. Here, foo is going to be an int. It's not going to be a reference to an int. And you can see that it's true because if I change the value of foo, the value of something has not changed. See, something had a value of 3, and it still has a value of 3, but foo has a value of 9 now. So foo and something, they are not actually the same variable. If you want to get a variable that would be a reference to whatever comes on the right, you have to use that auto ampersand notation that says that you want it to figure out the type and you want that type to be an explicit reference. And so now that bar is a reference to something, if you change the value of bar, you actually change the value to something as well. If you're wondering why people have auto, is it just because they're lazy and they don't want to write things? No, not really. There are two main reasons to use auto. One of them is because sometimes types can be quite cumbersome to write. For instance, iterator types in C++ can very quickly become very annoying to write. That one is actually still pretty simple, but they can get very long. And so you may want to use auto to figure out automatically what the types are. And it's also because in some contexts, you don't actually know the type of the things that you're manipulating. You don't know their explicit type, especially if you're writing like template class or template functions or things like this. You as a programmer do not know at the time where you write the code what the precise type is, but at the time where the compiler is going to compile that code, the compiler will know what the type is. And so you can use auto to tell the compiler, just pick whatever type it is, and that will do just fine. With that in mind, that's all I had for part 2. For part 1. Part 1 was really about the basics of the language, and part 2 is going to be about objects, so stay tuned. If you have any questions, feel free to ask in the comments.